welcome back. This is example 2 from 1 to day 9 for math. Oh, right. This is math 345, numerical analysis. Okay, so for example, the function that we're looking at here is f of x equals x times e to the x. And so we're given the data of these 5 nodes here. So at 1.8, 1.9, 2.0, 2.1, and 2.2. These are the corresponding values here. And so we're going to consider approximating the derivative of f of x at the point 2 using a 3-point and a 5-point method. Okay? So from 1 to day 9, the equation that we're using here is, I just want to make sure I get the numbers right. This is a formula 1. It's the top part, so I'm just going to draw like a little arrow here, and then this is the bottom one in that sequence. This is given for the endpoints, and this is for the points in between. Okay, so this is equation 1 in 1 a day 4. Okay, note that f prime is equal to e to the x factored out plus 1 times 1 plus x over here. And the value of f prime at 2 is exactly this 22.16168. Okay. All right. So if we take this formula then and look at our data and plug in our nodes, what we get is in the positive difference, we get 1 over 0.2. We have our nodes are 2, 2.1, and 2.2. And then when we evaluate this out, what we get is a value of 22.032310. And that produces an error of 1.35 times 10 to the minus 1, or about 13.5%. Okay. If I plug in here, if I plug in the value of h equal to -1, so this is the backwards difference, you get 1 over negative 0.2, and you get 2, our nodes are 2, 1.9, and 1.8. And this gives us a value of 22.054525. And that gives us an error of about 11%. Okay, those are pretty large errors given the values. So the other one now is consider the bottom from this. This is at the endpoints here, and let's see if that gives a better approximation. So if we plug in those values with h equal to 0.1, we get the endpoint value as 2.1 and 1.9, and that gives us a value of 22.223790. And that gives us an error of about 6% or so. So it's a better approximation. In this case, it's actually a little bit closer. Let's see what the next one does. So if we go to h equal to 0.02, we get the endpoints of the interval. Our actual values of the endpoints here is 2.2 and 2.8. We get the value 22.414163. And so that gives us then about a 25% error. So that's the largest error that we see so far. Okay, so now these are the 3-point methods. So you can see their 3-point methods are not as accurate as we might hope. So let's see how the 5-point process does. And though we have 2 references to 5 points in the notes, only one of them applies in this case. So we're only going to use the 5-point that looks like this. Okay. And this is because we don't have any additional information about the endpoints. So if we plug in our information here using a step size here of 0.1, plugging in the values 1.8, 1.9, 2.1, and 2.2, we end up with a value of 22.1669999. And you can actually see that one's going to give us a pretty close approximation just based on the actual value of f of 2. Remember, but this is the derivative of prime, and this is the derivative of prime here, and not the value. To be clear, I'm not talking about the value of f, I'm talking about the value of f here. So it's really close. And so in fact, it does show that the error here is 2 orders of magnitude better than the 3 points. So this is 1.69 times 10 to the minus 4th. So it's a significantly better approximation. for this f prime at the value of 2. And so a little bit extra, something that I think is kind of cool and we can use in the next example, or if we wanted to explore further down. The 5-point is a much better approximation, but we can also extend this process that we use to derive the 5-point and the 3-point to represent higher derivatives, higher order derivatives. This is very similar to the PDE approximation that we did in linear. And so that same scheme, in fact, is exactly what we're doing here. And so it's kind of cool to see cross references, if you will. And so if we consider the Taylor series, if we start with x naught and a step size, so we do a forward and a difference, right? A step forward and a forward difference. And then we create two series, f of x plus h and f of x minus h, specifically x naught, right? We're evaluating at a point. Okay, if we follow that schema, that idea, it is rather mostly algebraically intensive, but it is fun to go through. So I'll just kind of highlight some of the ideas here. Using a Taylor series expansion, we have f of x naught plus h, and we're expanding in powers of h, the variable that we're exploring around. Then you get out to third order this with an error term here. And then if you continue to expand that with f of x naught minus h, you get a very similar result, but you're going to see an alternating difference in signs. And so what's nice about that is if you then add the two together, first of all, note that x naught minus h is going to be less than your error term for the negative one, which is going to be less than x naught. And that's because you're going to be on your interval, you're going to be over here, and then you're going to be over here. So this is the string of inequalities is just really taking note about where you're at on that interval and where you're expanding about. So nothing magical there, but it is nice to kind of have a picture there. So if we add these two together, then we end up with a reasonably nice approximation for the second derivative. So you get f double prime is equal to 1 over h squared, and then you get the difference, and then these weights here, and then you get an error term there. Okay, and so at this point, with the correct assumptions on our function, we can use the intermediate value theorem and find a way to express these two individual error terms as an exploration of a single error term on this interval. Okay, and so if we do that, the fourth derivative evaluated at the point C is 1/2. It's the midpoint, if you will, of these two, which results in a really nice simplification here by, boy, that should not be that messy. So that using the intermediate value theorem with that assumption of shrinking the interval down, we get a simplification that allows us to write that in this interval from x naught to be between x, not x naught, sorry, c, yeah, no, x naught minus h and x naught plus h, that our seek value is somewhere going to be in that range. And that allows us to find or condense this into a single error term, which allows us to then create a much simplified version. So finding 2, we have a single value for the error approximation. So we know how good, or we have a handle on how close our approximation is to the actual value of the second derivative. Okay, so we were talking at the last one about just taking the second order derivative for higher orders and comparing it using the Taylor expansion. And so thought, well, why not just go ahead and do that with the example we were just working on? So this is the f of x. X is equal to f of x is equal to x e to the x. So the second order derivative we saw was 1 over h squared f of x minus h times minus 2 f of x naught plus f of x naught plus h. And then we had h squared over 12 f to the fourth epsilon. Okay. So the second derivative of our function is e to the x times 2 plus x, which means that f double prime at 2 was equal to 29.556224. Okay. So suppose that our estimate value, our step size is going to be 0.1, and we plug that in into the value, we get that our approximation for the second derivative is 29.593200, which produces an error given our value up here of about 3%. So it's a little underestimating by about 3%. So what if we try a larger step size? So let's double our step size from above. We plug that one in, we get f of 2.0. The second derivative of f 2.0 is approximately equal to 29.7047275, which gives us an error, a little bit significant, larger increase in the error there. So definitely doubling the step size did increase the error there. And so it's kind of interesting how much just by it's a hundredth, right? So we're just increasing, or not hundredth, sorry, it's a tenth. We're increasing the step size by a tenth. I mean, we are doubling the step size, but you get a significant increase in the amount of error, which led to a kind of an interesting little exploration that we have this competing factors that we need to attribute when we're computing these higher order derivatives. And so we have this competition that really plays out, and round off error is a particular menace for us as we get higher order derivatives. So let's explore this idea and consider the 3-point example. So if I pull out the 3-point example that we used in the earlier version of this example, we're going to consider the closed endpoint. Okay, so f prime of x naught is 1 over 2 pi, and then these are the endpoint values, and then we have an error term of h squared over 6 times the derivative of some value seq1 in that interval, and so we use the forward different values, right? So we're stepping forward and stepping back, and so part of the reason why we do that is that it encounters the round off error. So let's say that we have that term. So let's just name it as e to the x naught plus h, and then e to the x naught minus h, which correspond to the round off error from our step forward and then our step back in that situation. Okay, and so it means then that our approximation values are tildes, f tilde here for our forward difference and our backwards difference have these values, and they're related to the actual value of f evaluated the step size by the corresponding values of the error term. So f tilde of plus the epsilon, or the error term, and then f minus is minus in the error term there. Okay, so if that is, then the total error would be equal to the derivative minus the difference in the two approximations divided by 2, h, or step size, which is equal to the corresponding error in that value with the error term considered here. Okay, so if we assume that the bound of this error term exists, then there is some epsilon that's larger than 0 that creates a bound for the third derivative, which is also going to be bigger than 0. And if that's true, then we can say that the size of our error in this approximation is going to be bounded by this value here. So the absolute value of this error is going to be less than epsilon over h plus h squared over 6 times n. So this creates then that tension we're talking about with respect to the error challenges that we have in estimations for derivatives, that to reduce the truncation error, we need to reduce the step size of h. But notice that the round-off error is 1 over h. And so the smaller we make that step size, which reduces the truncation error, then the round off error becomes the dominant form, and so it blows up pretty quickly. So we have to play this trade-off between our step size being small enough that we limit the truncation error, but not so small that the round off error ends up dominating, and so we don't get a bad approximation. So this is an interesting conclusion that we arrive at as we explore the results of how error can propagate through our numerical estimations, and also the trade-offs we have to make in order to receive a reasonable approximation for the numerical derivative of a function. Okay, I hope this was helpful, and look forward to seeing you in the next video.